Hi everybody, I am Ayman from A to Z Physics. In this video we are going to talk about the atom. But first, please don't forget to subscribe to our channel and to activate the bell button to watch every new video. In this video, we are going to talk about the historical development of the atom model and differentiate between the absorption, emission, and continuous spectrum of light. Scientists have done experiments and learned more and more about atoms. They changed the way they think about atoms. We're going to show different ways that scientists have pictured or imagined atoms over the years. Let's first travel back in time to ancient Greece and talk about Democritus. Democritus first came up with the idea that matter is composed of tiny particles. He just thought that if you cut something in half for several times, you will reach a particle that cannot be cut anymore. He gave this particle a name, atomos, which means uncuttable. To explain how we know about what we know about the atom today, we should remember the English scientist John Dalton, who came up with the first scientific experiment that showed that matter was made of tiny little particles. After Dalton's model, an open question appeared: whether the atoms were like tiny billiard balls or were they made of smaller things. J.J. Thomson was able to answer part of that question when he discovered the electrons using the cathode ray tube. In the absence of any electric field, the cathode ray propagates without any deviation, while when an electric field is applied, the cathode ray deflected towards the positive plate. So Thomson concluded that these rays must be made of negatively charged particles, later called electrons. Thomson measured the ratio of the charge of the electron to its mass using the deviation of the cathode rays through electric and magnetic fields. According to Thomson's model, the atom is a large sphere of positive charge and the electrons are embedded in it. He found that almost all the mass of the atom is associated with the positive charge and not with the negative electron, and the diameter of the atom is of the order 10⁻⁻10 meter. Later on, Rutherford discovered that atoms have a nucleus with his famous gold foil experiment. In this experiment, a ray of alpha particle, which is positively charged, is directed through a hole towards a golden foil surrounded by a circular flash detector. A closer look at the video shows that most of the particles penetrate the foil without any noticeable deviation. Some particles deviate from their original path, and few particles recoil from the foil with an angle of 180 degrees. So Rutherford observed that most of the particles penetrated the foil without deflection. Based on this observation, he concluded that most of the atom is an empty space. Some particles deviated from their original path, so he concluded that alpha particles hits a light particle, causing this deflection, which is the electron. Few particles recoiled from the foil with an angle of 180 degrees, so he assumed that there must be something very small but very hard inside each atom, which is the nucleus. According to Rutherford, the atom is a spherical of central part. Nucleus carries most of its mass and it is positively charged. The electrons revolve around the nucleus in a motion similar to that of the planets around the Sun. In 1913, Niels Bohr proposed a model for the hydrogen atom that succeeded in explaining the regularities of its spectrum. What do we mean by a spectrum of light? In fact, there are three types of spectrum: continuous, emission, and absorption spectrum of light. Let's first begin with the continuous spectrum. When a beam of white light traverses a prism, the various wavelengths are separated into a continuous spectrum. So, when a sunlight giving out all wavelengths of light passes through a prism, you get a continuous spectrum that shows all wavelengths of light. The discrete emission spectrum. If the light emitted from a glowing gas under low pressure, for example hydrogen lamp, traverse a prism, the obtained spectrum is formed of sharp and discrete parallel lines showing selected colors of specific wavelengths. The emission spectrum is formed of colored lines on a black background. First, you need to energize the hydrogen gas, perhaps with heat or electricity. It then releases light, passes through the prism, and hits the screen, leaving the line spectrum behind. The absorption spectrum. If we direct an intense white light which contains all the visible radiations on a gas, the gas absorbs certain photons from the incident white light, and the light traverses the prism. The obtained spectrum is formed of discrete dark lines on a bright band of colors. In this case, the spectrum is called the absorption spectrum. The absorption spectrum is formed of dark lines on a colored background. These lines are discrete, discontinuous, so there are specific value missing radiations of wavelength lambda. If we place a hydrogen gas between the source and the slit, the hydrogen gas will absorb some of the radiations, so the electromagnetic radiations leaving you with the absorption spectrum, which is a continuous spectrum of light with selective missed wavelengths. Bohr's model of the atom. Based on his observations of the discrete emission and absorption spectra of the light emitted and absorbed by the hydrogen atom, Bohr postulated that each atom has its own set of unchangeable discrete energy levels. Each level is associated with a quantum number, n equal 1, 2, 3, etc. n equal 1 corresponds to the ground state or fundamental state, n equal 2 corresponds to the first excited state, n equal 3 corresponds to the second excited state, and so on. The atom can have energy equal to one of these levels. Electrons in the electron cloud of the atom must be in one of those energy levels. Any intermediate energy between levels is strictly forbidden. The electron here cannot be in a place between these two energy levels. It must be at one of these levels. The energy of the atom is quantized. The energy of the atom cannot have any value. It can only take some particular values. All isolated atoms of the same element have identical set of energy levels, while atoms of different elements have different sets of energy levels. As we saw in this picture, we have two energy diagrams for two atoms, the lithium atom and the mercury atom, and we can observe that each of these atoms has its own set of energy levels. For example, the ground state for the lithium atom have an energy equal to minus 5.39 electron volt, while the ground state for the mercury. Bohr's model suggests that The atomic spectra of atom is produced by electrons gaining energy from some source jumping up to a higher energy level, as we see in this demonstration, then immediately dropping back to a lower energy level and emitting the energy difference between the two energy levels. So, when an atom passes from one energy level, En, to a lower energy level, Ep, or when it passes from one energy level, Ep, to a higher energy level, En, it emits or absorbs photon, whose energy is equal to the difference between the two energy levels. En minus Ep equal h times frequency, or En minus Ep equal hc over lambda, the wavelength, and of course En must be greater than Ep. En is a higher energy level than Ep. And note that no photons are emitted or absorbed as long as the atom remains in the same level.